Hello guys! So in this demonstration we will continue going over forces that act on particles. Consider the following box that is supported on a table. The following force that we will introduce is the normal reaction of support. The normal reaction is the force that is perpendicular to the supporting surface when the object is in contact with the surface. This is the force that the surface exerts on the object to support it still, and it is perpendicular to the supporting surface. In this case, the normal force is vertically upwards and is perpendicular to the table, making a 90 degrees angle with the table as shown. The magnitude of this normal force, or this normal reaction, if it is in the opposite direction of the weight, along the same axis, is equal to the weight of the supported object, say the box. So let's designate the normal reaction with the uppercase N. The weight of the supported object in this case is acting vertically downwards, perpendicular to the ground, so opposite to the normal reaction, and is designated by F. Then N is equal to F. The normal reaction is equal to the weight exerted by the box on the table. The normal reaction is the force exerted by the table on the box, since N acts in the opposite direction of F. N is perpendicular to the table and acting upwards. So that was the normal reaction. Next, we will introduce the tension force. This is the pulling force exerted by an object pulling another object. So let's consider the following example to understand its concept. This is a ceiling with a hanging rope, where an object is hanging at the end of this rope, a rope or a string, let's say. So this rope is called a string, which is what mostly exert tension. So in most examples, we will observe tension exerted by strings. So for the hanging object to remain hanging and not fall down, the string should be exerting a pulling force on the hanging object. This pulling force is the tension force, designated by F tension, or say an uppercase T. So this is the third introduced applied force. There is the frictional force, that is the result of the contact between two rough surfaces. There is the normal force, that is the perpendicular force that the surface applies on the supported object in the upward direction. Finally, there is the tension force that a string applies on an object to pull it in a certain direction, as in this hanging object that is hanged by a string exerting a tension force. The fourth force is the thrust or compression force. Compression is the force that obviously compresses an object, thus decreasing one of its dimensions. To understand this, consider the following example too. Consider the spring that is supported from one side, so it's supported from the left side. This spring is compressed to the left by a force that shrinks it to this size as shown. This applied force is the thrust force, F thrust, or the compression force, F compression. So this is added to the friction force, the normal force, the tension force, and this is the compression force, which are possible forces acting on an object. And for a compressible object like this spring, the force opposite to tension is the force of compression. Meaning that if we apply a force opposite to compression that elongates the spring or increases its length, this will be a tension force. Notice that a string or a rope is a non-compressible object, since if we attempt in the example of the string to apply a force upwards by the ball, the string will become loose, while we can only pull it downwards and apply tension that in turn would pull back on the hanging object and keep it hanging. So it's the pulling force pulling back on the hanging object and keeps it hanging. Next, we will consider the gravitational force or the force of gravity. So gravity is the force between any object present on Earth and Earth. So any object present on Earth would create a contactless force with Earth. The direction of this force, the force of gravity, is always directed from the object perpendicularly towards the Earth. So consider this ball that is released at a certain height from the ground or from Earth. Then the developed gravity between the object and Earth that is pulling downwards on the ball towards Earth and which is perpendicular to Earth or perpendicular to the ground will force the ball to fall down. So if we throw the ball upwards, the ball shall fall down by the effect of gravitational force. So the force due to gravity acting on an object is what we call the weight of an object. Weight is always acting vertically downwards, since Earth is downwards and Earth pulls down any object present on it. So any object released at a height from the ground falls down under the effect of its own weight along a vertical direction perpendicular to the ground and not in any other zigzag direction. So a body falling freely experiences an acceleration g, which is equal to 9.8 meters per second square. This means that an object falling only under the effect of its own weight accelerates at a rate equal to the gravitational acceleration. So g, 9.8 meters per second square, is the gravitational acceleration. Then if we apply Newton's second law to a free falling object in order to determine the value of weight, we apply Newton's second law to a free falling object where nothing is acting on the object but its own weight. So the net applied force is equal to m multiplied by a. This is Newton's second law. This is the equation of Newton's second law. In this case, the only applied force, as we said, is the object's weight w. W, thus, is the net applied force. That's equal to ma. And a in this case is equal to g, since the acceleration of a free falling object is the same as the gravitational acceleration g. Thus, the force applied on an object due to gravity present on Earth is the weight of the object, which has just been proven to be equal to mg by Newton's second law. And this is the fifth force along the other four previously considered forces that can be applied on objects.